So welcome everyone after for the third talk of the morning session. So we have Professor Sumilan Banerjee from Indian Institute of Science telling us about superconductor-insulator transition in weakly monitored Josephson junction arrays. So
yes, thank you, Divas. Okay, so let me start thanking the organizers for giving me opportunity to speak here. So I'll be talking about something related to like measurements in quantum many-body systems, but not too much looking into the quantum information aspect of it, at least for this talk. So okay, so this is just to sort of set the thing. I mean, there are several. I mean, a lot of talks about measurements and entanglements, but just to sort of tell what I'm going to talk about is this basic idea that when you just measure, let's say, just a single particle states, then of course you collapse the wave functions with probability half in this case. Similarly, as we have seen that if you take a entangled state like a standard some Bell pair, one of the Bell pair states like this one, which has an entanglement entropy log 2, then again if you measure one of the qubit locally, then you either get one of these states and again with probability half, but the most importantly this unentangles the state. You start with the entangled state. So the question that I'm going to discuss, of course, so there are two things that one, I mean, at least the most popular thing that people ask in recent times is that if you now do these measurements on many body systems, I mean, if you have many body system, probably you have to do extensive number of measurements, maybe many times. But if you do that, then how do you change the nature of the many body states, the entanglement structure of the many body states? So for example, if you have some states which has volume law entanglement as a caricature, a lot of Bell pairs across a subsystem and the rest of the system, essentially the proportional to the number of the size of this subsystem, and then you do the measurements and you get into this area law entangled state. So that's the entanglement transition. But the particular question that I'm going to discuss with the effect of measurement is not this one, although I'll discuss a little bit of this one, but just to motivate. But the question that I'm going to ask is that, I mean, can you use measurements to manipulate conventional phases? So for example, let's say if you have an insulator, can you do measurements, make it a superconductor? Okay, or let's say take a metal and make it an insulator. A superconductor, make it an insulator by doing measurements on a many body system. So okay, but before that, again, so this also in the morning talk, this unitary gates with measurements we heard. But just to tell the, so this is the lot of work on this measurement induced phase transitions, where you have this type of circuits with some input qubit state, these legs, and then you have some entangling gates, which are these green boxes, which entangles. So if you only have these 2 qubit gates alternating between alternating qubits, then it will generate a lot of entanglement at long time, typically volume law. However, you disrupt this by doing some local measurements. For example, just measure SG component of these qubits. So then locally it will destroy it, and you can now have a competition between these measurements and the entangling unitary by deciding how many per instant of time, how many of the qubits you measure. So that essentially is the number of qubits that you measure, which in some sense is the measurement rate in this case. And by tuning the measurement rate, you can tune a phase transition, as we know by many works there. And the main important point there is that you get very interesting critical points, which has properties, so dynamical critical points, which has properties like the standard critical phases in standard quantum many body system, going from this volume law to area law entangled state, as shown here, that when you don't have any measurement, P is 0, measurement rate is 0. So then in a 1D system, you get this volume law, that is the entanglement entropy scales with the system size as L. And then as you do more and more measurements, ultimately it goes through a critical state with some kind of logarithmic behavior into area law, which eventually saturates for large system. Okay, so that's the transition. So this is the main motivation, but as I said that I'm not, so the model that I'm going to discuss, of course, you can ask similar question in that model, but in that case, what you need to do is that you have to look into, so here, for example, to see this entanglement transition, you have to look into typical trajectory. And that is hard because of these post-selection problems and all. So what I'm going to talk about, the transition that I'm going to talk about will happen in a trajectory average sense. Okay. But it will be also a measurement transition, but not measurement induced transition in this sense, in the sense of entanglement transition. Okay, so this is the work that I'm going to discuss. So this is all done by a very brilliant undergraduate student at IISc, Purnendu. So this is related to Josephson junction arrays and basically monitored Josephson junction arrays. So let me just introduce a little bit for the general, given the broader audience here. So these Josephson junction arrays are essentially a realization of quantum XY model. So you have originally in physical realizations, these are some kind of superconducting islands shown by these red circles. And so these are in physical realization, they are mesoscopically large, and so they have some well-defined gap, superconducting gap, but they are still finite size. So there is some fluctuations of the Cooper pair number on each island. As a result, there is a commutation relations between the phase of a given island at site I and the number of Cooper pair on that island. And then these islands are coupled by some weak links, some Josephson links, which are described by this term, the Josephson term. And as a result, there will be a competition between this term, which doesn't commute with theta, and that competition lead to quantum phase transition. So this is a very standard model of quantum phase transition, and this is realizable in artificially created Josephson junction arrays on these some aluminum superconductors, and then you create these islands and then weak links and all. And the main thing that you find is that there is a superconductor-insulator transition in this system. So namely, if you tune this this ratio between this charging energy, this EC and J, then you can induce a transition, and this is in fact seen in experiment where you can see that there are some insulating state, and as you tune some of the parameters, you can go into some superconducting state across a quantum critical point. And this in theoretically also you can calculate, looks like a standard quantum critical phenomena going from as a function of this charging energy to the Josephson energy, you go from a superconducting state to an insulating state. Okay, so now I'll be going to discuss the case when you have measurements, but let me just to orient it. So let me just say that how do you sort of theoretically at a very basic level, how do you get this kind of phase diagram? So the standard method, of course, in condensed matter, you can use the single side mean field theory, effectively just decoupling this Josephson term. And then you can just do a mean field calculation, and you will find that there is this transition, mean field quantum phase transition from an insulator to a superconductor, and you can look at the order parameter or superfluid stiffness, how it changes across this transition, etc. So we are also you can do slightly better approximation, which is better in some regions, namely in the superconducting state, which are called which is also a variational approximation, which is called the self-consistent harmonic approximation. And here what you do, you again try to reduce this interacting problem into a solvable problem. So rather than a single side problem, you reduce it to a harmonic chain. Okay. And then you have a variational parameter, and again you can calculate this variational parameter, which is the phase stiffness variationally by minimizing the free energy, and then you will also get a superconductor insulator transition. However, typically this approximation is not very good close to the transition, typically gives you first order phase transition. Okay, but we will be using this kind of methods. So, so the phase transition that I will be talking about, you have to take it with some pinch of salt. I'm not really going to look into the real nature of the phase transition. because I'm going to do this type of approximations. But the robust features of the phases I expect to be same using this kind of approximation, which I'll generalize for the measurement case. Okay. So now let me come to the sort of the main question that we are asking here. So now even in this Josephson junction, what I showed you was an isolated system. But typically when you make this system, the Josephson junction array, so there is always some environment. And also these are realizations of granular superconductors where you have really real material where you have superconducting grains, not artificially created, but superconducting grains, and that are connected by weak links. So in all those cases, typically you will also have some dissipation in the system. In fact, there was this experiment in a very long time ago in 1980s, where people found that below a certain critical threshold of normal state resistance, which essentially controls the dissipation in the material, the transitions basically become independent of the Josephson coupling, etc. Right? So essentially, it looks like some thermodynamic transition was controlled completely by dissipation. Okay. So this was a puzzle, and again, I don't know the resolution of the puzzle. I mean, there are a lot of works on this. So I'm not going to go into the issue whether this experiment really is controlled completely by dissipation. But this was a motivation to study dissipative Josephson junction. And the famous work, I mean, there are several works, but the work that I know of is by Chakravarti, Kibelsons and others, where what they did is that they generalized this Josephson junction model by coupling it to some caldera-Leggett type ohmic bath. So essentially, you have same Josephson junctions. Now, what you do is you couple this phase difference of these Josephson junctions, which are some gauge invariant quantity, to some oscillators, some bath of oscillators. And then this bath of oscillators is in thermal equilibrium at some temperature T. Okay, so this system is an equilibrium system with a thermal bath, and there is a kind of a quantum thermal dissipation here. You can take low temperature limit T going to 0, then you will have some quantum dissipation, but still equilibrium dissipation. Okay, and you can find out the phase diagram. So for example, you can integrate out this bath, and then you can get effective action for this dissipative Josephson junction, which is controlled, the dissipation is controlled by this dimensionless constant alpha, which is essentially given by the normal state resistance. Okay, so now you can study the phase diagram as a function of this Josephson coupling and alpha, and theoretically using this self-consistent harmonic approximation, this is what these people found. So now you have two axes, Josephson coupling divided by the charging energy. So when you have zero dissipation, this was the quantum phase transition. Now, as you are tuning the dissipation, of course, what happens, you find that in fact, as you increase the dissipation, superconducting state get enhanced. So meaning that you get a superconductor for lower value of Josephson coupling. Okay, and this happens in this model because of the particular nature of the coupling. So the coupling is to the phase difference. So in some sense, this dissipation is trying to fix the phase difference. So if you fix the phase difference, then you are trying to sort of competing against this quantum fluctuation because of the Cooper pair number, and as a result, dissipation in this model in fact enhances superconductivity, at least at zero temperature. Okay, and in fact, if you increase the dissipation above some critical value, then what you find that you get even at zero, almost at very infinitesimally small Josephson coupling, you get a superconducting state just induced by this dissipation. Okay, you can see this phase transition. Of course, within this approximation, these are first order transition, but that's not very important. What is important is that the dissipation actually stabilizes superconducting state here, and in fact, there is a universal, at least within this approximation, this transition happens at a universal value of this coupling, which just depends on the dimension of the space. Okay, and in fact, this is the result they tried to explain. As I said, that below certain so if once you go this, you increase the dissipation certain amount, then you see that this transition doesn't depend on the Josephson coupling. So it becomes independent of that. So that was the motivation of this work. So essentially dissipation manipulating a thermodynamic phase transition. Okay. So now I'm going to change this. So I'm going to put a dissipation, but it's a different type of dissipation. So we'll try to understand what dissipation is, but before that, let me just discuss the model. So this is a model of certain model. I mean, it's not a general model, but some fairly well-known type models that has been used in this literature of weak quantum measurements. So that I'm going to discuss or generalize to this Josephson junction. And what I'm going to ask, I'll describe the model in details. What I'm going to ask is that, so in this model also you'll see that there is some dissipation because of the measurement process, and also we'll see that we'll need some feedback in this system to control the heating of the system. So in some sense it will give a dissipation, but this dissipation, nature of this dissipation, as I'll argue, will be very different from this thermal or quantum dissipation in the caldera-Leggett case. Okay, so what is the model? Okay, so the pictorial it is shown here. So again, I am showing for convenience a 1D Josephson junction array. So these are these islands which has these phases, and important thing is the phase difference. And then these phases doesn't commute with the Cooper pair number. So that's the basic ingredient of this model. Now the particular measurement setup that I'm going to consider is this. So what I'm going to do is I'm going to now couple this system periodically in some sense with some period tau to set of detectors. Okay, so these detectors are again some quantum particle which is shown by this here Gaussian wave. So these are quantum particles. So this is like a particle with a position and momentum, and their momentum is shown here by red. So this particle lives on the bond, so that's why they have an index ij, and these particles are in some brought into the picture at each instant of time, which is where I am doing the measurement at n tau. Okay, so I am doing measurements periodically like this, and I am bringing some detectors. Now what does the detector do at time n tau? It couples to the system the gauge invariant phase difference through its momentum. Okay, so this quantum particle is getting coupled. I have still not done any measurement. I am just entangling the detector at that instant of time with the Josephson junctions through coupling to this phase difference. Okay, and in between two measurements or two interactions, the system just evolves with the Josephson junction Hamiltonian that I showed earlier. Okay, so this is the setup. So now what is the measurement? So to do the measurement, I first prepare the detector in a special state. This is because of convenience of calculations. So you prepare the detectors into some Gaussian state. So these are quantum particles with position and momentum. You prepare them in a Gaussian state, and then what you do at this instant of time, they get entangled by this interaction, this delta function interaction with the Josephson junctions, and then slightly later Tn plus n tau plus, what you do, you projectively measure this quantum position of the quantum particle. Okay, so if you projectively measure this, so then you collapse this detectors, this quantum particle, and you get some reading, some trajectory of reading at each instant of time n and for each bonds, right? So that's the projective measurement, that is the reading that you get. So this is not directly collapsing the system, it is collapsing the detector, but since the detector is coupled to the system, it will have a non-unitary effect on the system. Okay, so it will affect the system dynamics. So how does it affect the system dynamics? So the way it affects is, again, you can write down some density matrix evolution. So for example, the total density matrix just before the nth measurement is a product state of the density matrix of the system before that time, which depends on all other measurements that you have done till that time, okay, which is t plus n minus 1, and then some unitary evolution. And then it is, so you brought this detector, new set of phase detectors which are in this product state with the system. Okay, so now what you do is you interact the system with this detector, so that interaction gives rise to some unitary part which comes from this delta function, so you have a unitary part, and then you project the detectors into some position state, so you apply a projection operator. So that is the density matrix evolution of this non-unitary. Yes, this is quantum state diffusion. Yeah, you can write a quantum state diffusion model. Okay, and then you look into the density matrix of the Josephson junction only. So you trace out the detector. So you just trace over the detector thing, which is because basically just like projecting. Okay, so that gives you the density matrix, and that density matrix you can write in this form. So you have the density matrix earlier, after the earlier measurement at n-1, then there is some unitary evolution, and then there is some non-unitary Krauss operators, okay, which is obtained by doing the process that I mentioned. Now it turns out that in this model, if you go on doing such measurements, and I'll show that it actually heats up to very high temperature. Okay, so it's indefinitely heats up. And now to control this heating up, there are standard methods in these quantum measurements, which is that you apply some feedback, and the particular feedback you apply has this form. It's a unitary operator. So you know your reading, and using the reading, you try to feedback so that it doesn't go indefinitely, the heating of the system. And I'll show that how it controls the heating of the system. But right now you just apply this feedback. So that is the whole operation, right? So apart from the measurement, which gives rise to this Krauss operator, which is non-unitary, which tries to fix the phase difference to the measurement outcome, you have this unitary operator, which has a strength gamma. And this gamma, I'll show that it acts like a dissipation. Okay. So now to look into this system, we take a particular limit of this, which we can easily write a path integral, which is that you take, so I mentioned to you about this Gaussian. So this Gaussian has a width sigma. So what you do is you take this width to infinity, however you do the measurement too frequently, tau going to 0. So this is called a continuous weak measurement. So essentially the weakness of measurement is controlled by sigma. If you make sigma larger and larger, measurement becoming weak. But it is too frequent because I am taking tau going to 0, keeping this product fixed. Okay, and if you do that, there is a well-defined limit, and this delta inverse gives you a measurement strength. Okay, so you can tune this measurement strength, and in this limit, you can write down a path integral in a Schwinger-Keldysh way for this non-unitary evolution. You can write down a generating function. Okay, and this generating function depends on all the measurement outcome till that time. Okay, so now so this generating function is actually nothing but the bond probability of the trajectory. Okay, so essentially it gives you the bond probability. So each trajectory, so you do many measurements for a long time and you get a trajectory, and that trajectory, the bond probability is given by that. So that defines the quantum trajectory, and this is the weight corresponding to that trajectory. You can get by the process I mentioned, you get an action for this field theory, and this action depends on the measurement outcome, and then this Krauss operator appears here, the Josephson coupling, the charging energy, everything is there. Okay, so that's the action. And what we assume is that we only assume that we are going to study the long time steady state. So you assume that there is a long time steady state independent of the initial density matrix. This of course we cannot prove, but this is an assumption, and you assuming that we do all the calculation which is for the steady state. Okay, so now of course this is an interacting model. I can't really solve it just like in the equilibrium case. So I'm going to do a approximation. So that approximation we do is the generalization of the self-consistent harmonic approximation. So what you do is you write a variational action with some variational parameter which looks like some kind of superfluid stiffness, and then what you try to do using this variational answers, you try to maximize the bond probability for a given trajectory. Okay, so that's like defines a free energy. So of course here there is no free energy because it's just a time evolving system, but you can define a bond probability and some corresponding free energy, and you can write down a variational answer for this, and you can find out the variational principle and the variational function that you have to minimize. If you minimize, you will get this self-consistent condition. Okay, just like in the equilibrium case, the standard case. And now what you do, you assume that it is a steady state. That is that this object will become independent of time, and also a translationally invariant system. So it will become independent of ij, and in this also you now we look into trajectory average quantities, and then if you do that, then this is the self consistency condition that you get the superfluid stiffness given by this quantity, which itself depends on the superfluid stiffness. Okay, and it is determined by this action. And if you will get a superconducting state, if you have the stiffness 0 or non-zero, and then you get when it gets 0, it just that gives an insulator. Yes. Yes. Right. Right. Yeah. It's just, so given a particular trajectory, it tries to maximize the bond probability. So it's trying to find the maximum probable trajectory. Yeah. Okay, so you can, okay, so if we are looking into trajectory average quantity, then you can look at to this trajectory average generating function, just like in the standard Keldy's case, it is actually 1, okay, because I have averaged over trajectories. And actually this evolution you can describe by a Lindblad evolution, although you are not using it. And you can calculate the observable like this by averaging over the fluctuating field and also the measurement outcomes. Now what happens, at least in the trajectory average case, that you get a effective action that describes this, this generating function. And the nice thing is that once you do the trajectory averaging, even though the system was non-unitary and all these things, you get a causal structure of the action. Okay, so essentially you get the same causal structure that you will get for unitary evolution, which is encoded into this Keldysh-Green's function, the retarded advance and the Keldysh-Green's function. So that is a nice thing. So these have the causal property once you average. Of course, if you don't average, then they will have some, you have to regularize it properly, which we are not doing here. Okay, now let me come to the results. So what do you get from this? So we solve this, and this is the phase diagram. So now what we are plotting here is the Josephson coupling versus the measurement strength, and what you find is that again there is a superconductor to insulator transition, but now I have this kind of very weird looking phase boundary, which looks like a reentrant phase boundary. Okay, so in some sense that when you have very low measurement, then you have the standard sort of transition, and then as you increase the measurement rate, it first goes from an insulator to a superconductor, and then it goes across it and again goes to an insulator. Okay, so the phase boundary is quite different, as you can see from the dissipative Josephson junction I show. And why is that? So you can kind of understand this from the idea of dissipation and the nature of the dissipation in this system, and that you can track using a effective fluctuation dissipation ratio. Okay, so as I said that this has a causal structure even in this measurement case, and what you can do, you can now try to compare your dissipative model, which comes from equilibrium dissipation, thermal or quantum, the Caldera-Leggett model studied by Chakrabarty et al., and this model. So if you compare, you can see that there is a equivalence between the feedback that I gave. So remember I gave a feedback, so the feedback can be compared with the dissipation. Okay, they have very similar structure, this Green's function. However, where they differ is this fluctuation dissipation ratio. So you can obtain a fluctuation dissipation ratio by taking a ratio of this Keldysh-Green's function to the difference of retarded and advanced Green's function. And in this measurement monitored model, this is exactly given by this quantity, okay, in the model that I discussed. So it has this some kind of effective temperature, as you will see that why I am calling it effective temperature. So some kind of effective temperature which is given by this, and then there is a second term. So now you can compare with the dissipative case. So dissipative case, of course, the standard fluctuation dissipation ratio will be some Caught hyperbole. That's the general fluctuation dissipation, and if you take a high temperature limit, then the first term will be 2T by h bar omega. Okay, and that is exactly same here. However, the temperature that appears here, it is temperature of the thermal bath, but the temperature that appears here is nothing to do with any bath. It is completely controlled by your measurement strength and the feedback. Okay, and that's why I was telling that you need a feedback. If you take feedback to 0, gamma to 0, as you can see that this system will heat up to infinite temperature. So that's why we applied a feedback. So this is, you can compare it something called a quantum heating. So there is no real thermal bath here, but the system appears to be in a mixed state with a temperature, okay, which is completely generated by the measurements and the feedback. However, the main difference between the two cases is that if you expand this series of Caught hyperbolic, it will have many more terms, but this just truncates into the second term. And in fact, when you go to low temperature, this series you have to take fully, the Caught hyperbolic series. But this, even at low temperature, where the first term is not only dominant, second term is also important, it just truncates to the second term, and that turns out to make this huge difference. Okay, so the fact that the fluctuation dissipation ratio, especially at low temperature, where this full thing should be compared with the full thing here, makes a real large difference. Okay, and that turns out to give this very different phase diagram. So the dissipation in both the cases, dissipation in some sense in the measured model is controlling this, whereas here this is the thermal dissipation, but the phase diagram you can compare, you have a re-entrant transition. Now you can try to compare them slightly differently, which makes it much more clear, which is in terms of a temperature versus a coupling for a fixed dissipation strength. Okay, so I said that there is a effective temperature which happens at high temperature or some low energy. There is a effective temperature for the monitored model, and in the dissipative model there is of course a temperature which is the temperature of the bath. Now if you look at the phase diagram here, so this is the phase diagram. So at T equal to 0 you have a quantum phase transition, and as you go to higher temperature you need larger Josephson coupling to go get a superconducting state. So that's the standard thermal transition. Okay, so you are going from a low temperature superconductor to a high temperature insulator. So that's the finite temperature superconductor normal state transition. However, here what happens is quite strange. Here what you are actually getting is a low temperature insulator and high temperature superconductor. Okay, so you are actually, by increasing temperature, this effective temperature, you can go from a low temperature insulator normal state to high temperature superconductor. Eventually, of course, if you go to very high temperature, it will be destroyed. This line will come and it will again go to an insulator, but there is a in between. So you can actually have a transitions from a zero temperature insulator to higher temperature superconductor in this model. And this is of course a MIPT. I mean, this is some kind of MIPT, not the standard MIPT, but this is kind of a weird outcome. Now, so now, okay, so this is the, so of course these results are all obtained using this self-consistent harmonic approximation. So you can ask what is the validity of these results beyond this approximation. So in some limit you can actually study this model without making this approximation. So one such limit is what is a semi-classical limit. Okay, so if you look at the semi-classical limit, then this self-consistency condition, a semi-classical limit essentially when this T effective is very high or H bar in some sense is very small. Okay, so then you get this the self-consistency condition I showed reduces to this. Now it turns out in this limit you can actually derive from this Keldy's theory an effective classical description, which is by expanding the Keldy's theory in terms of the quantum and classical component. You can expand the Keldy's action, and it's essentially an expansion in H bar, and you can obtain the sort of the fast quantum corrections, which what happens, it looks like essentially a Langevin equation. So you, in this limit you get a Langevin equation, just like a garden variety Langevin equation, by doing this calculation. So here I am not doing a self-consistent harmonic approximation, I am just deriving a semi-classical approximation. And in the Langevin equation you exactly get this noise which is controlled by this effective temperature that I showed you earlier. Okay, again this Langevin equation is completely coming from a measurement process. There is no bath or some stochastic thermal bath here, but it looks it is identical. If you identify this temperature, this Langevin equation is identical to the dissipative case. There is no difference. You will not be able to see any difference. And in fact, this transition over here, which is at high temperature, is exactly the thermal transition that you will see in a thermal ensemble. And as a result, if you change dimension, for example, if you go to 2 dimension, this transition would be a BKT transition, just like standard case. And in 3D, it will be 3D XOR. Okay. So this is, so at least this high temperature limit, you can understand that this phase diagram is correct. I mean, it's not dependent on this approximation. We can do also look into some other limit where you don't need to do this high temperature thing, which is this what is called a strong feedback and measurement limit, where this feedback and measurements is much larger than J or EC. So in this case, what you can do, you can actually split this action into some fast and slow mode, where the cutoff is given by one of these numbers, for example J by m gamma. So essentially you can define some fast and slow modes, and you integrate out the fast mode and again obtain some effective action, and you will again in this way get a Langevin equation without doing the semi-classical approximation. And in the Langevin equations, when you integrate the fast mode, what you find for the slow mode, there is a effective Josephson coupling, And this effective Josephson coupling actually now gets renormalized because of integrating out of the first mode. And what you find that indeed, as you increase this measurement strength or the dissipation strength over here, you see that this effective coupling goes to a negative value or approaches 0 and then negative. So that means the superconducting state will be unstable, and that is the reason here at very large dissipation or large measurement, unlike the dissipative Josephson junction case, you actually have an insulator. So remember, the earlier dissipation actually stabilizes the superconducting state, large dissipation. However, here because of this different behavior, the feedback or the measurement actually stabilizes the insulating state. So that you can see here, and it's very different from the dissipative case, where if you do the same procedure, you will indeed see that dissipation ultimately induces a superconducting state. Here, however, the effective coupling is different. It goes to 0 at large values of feedback, and it doesn't happen. So you can do this process iteratively, essentially a weak coupling RG, and you can obtain the flow equations for this Josephson coupling. And what you will find is that, so essentially similar method. Now you do is systematically, that you integrate out some fast mode and slow modes using J as a small parameter, the weak coupling RG, and you get these RG equations. And what you find is a very similar reentrant type behavior, okay, by these RG. So this is just to show that this kind of reentrant phase transitions is not just a artifact of the cell consistent approximation. You get it even beyond that. And you can see that this is very different from the dissipative case again. As I said, so in the dissipative case, if you do the same RG, then you will find that the beta function becomes negative when your dissipation strength alpha is greater than 1 over d, which was this result, that beyond this you always get a superconducting state, it flows to strong coupling. Okay, sorry, it becomes positive, so it flows to strong coupling. Whereas wherever the flow to strong coupling is this reentrant region, and it is surrounded by these regions where you will expect a weak coupling result, meaning J going to 0 and an insulating state. Okay, so this is what you can get this. So now, so that's basically the end of the thing that I wanted to discuss. Now let me just say that there are some connections to this with already some well-known work. Since I have 2-3 minutes, let me just mention this. So this, what I discussed in this measurement setup, in some way, in slightly different way, has been discussed from more open system setup, or in other words, this driven dissipative system by this kind of famous works by Sebastian Diel, Peter Joller and others, which is this general theme of manipulating quantum states by engineering bath and dissipation. Okay, and the model they considered, they of course didn't look into an explicit measurement setup. They looked into a Lindblad setup, which is the standard Lindblad equations with the Lindblad jump operator here and the density matrix of the system. And what they took is a Bose-Hubbard model. Okay, so they took a Bose-Hubbard model with some interaction, and the particular jump operator, which they argue can be designed in a optical lattice setup, that took was this form. This jump operator was of this form: AI dagger plus AJ dagger and AI minus AJ. Now, what is the connection of this with our work? So you can actually see the connection. So first of all, in this work, what they show that if you have a non-interacting limit, meaning only this term, then of course, if you don't have any jump operator, then it will be a BEC. Okay, so if you at 0 temperature, this system will have a BEC. Now, what they showed that even when you are non-interacting, but you introduce this bath, because of this particular form of this bath operator, which is AI minus AJ, so what you can show that this BEC is actually a dark state of this Lindblad equation. So essentially, if you act this AI minus AJ on BEC, it gives you 0. So it's a null state of this operator, and this is also eigenstate of the Hamiltonian. So that is the criteria for a dark state. So as a result, in the non-interacting case, this goes into a BEC or a condensate, and you can see what is the connection that I am talking about. So this operator is essentially, you can, if you look into some kind of a phase language, is like e to the power I theta I minus I theta j. which if you expand is like theta minus theta j, and that is exactly what is happening in our case also. So this phase difference is by repetitive measurement, you are trying to fix this phase difference, and the Josephson coupling is giving you this phase coherence. Okay, and that's exactly same thing happens there. But what is different from this case is that in their case, if you as soon as you put some interaction, then you can show that this dark state is destroyed. In fact, you get a weakly mixed BEC, which is at some temperature, which is again there is no bath as such, there is no thermal bath as such, but there is an effective temperature that emerges, which is controlled by the interaction strength and the number density or the chemical potential. Okay. So of course, in our model, this is different. So what happens in our case is that we are not controlling the temperature by the chemical potential. So they essentially in their system, it doesn't heat up because there is a chemical potential. You control the number, and the number controls the effective temperature. So in our case, of course, we have a Josephson junctions, effectively unbounded number of Cooper pairs. Josephson, the superconducting island, unbounded number of Cooper pairs. So here what is controlling the temperature is this feedback. Okay, so it's not controlled by the interactions, and as a result, so this is the phase diagram they had, that effective temperature. So if you go above certain interaction strength, then you get normal state, but if you come below, there is a weakly mixed BEC, and then when you have zero interaction, you have a dark state. Okay, so in our case, the situation is different, and because the temperature is controlled by the feedback, you can get a very different phase diagram from that what they realize. So it sort of opens up window to look into much richer phase diagram than considered in this work. So with that, let me summarize just to say that I mean, if you look into this, so what I discussed is this particular weak measurement model, where by manipulating the system by measurement, you can actually have very interesting outcome. For example, you can convert an insulator into a superconductor, and in fact, a low temperature insulator to a high temperature superconductor. Thank you.
So let's thank the speaker. Thank you for the very nice talk. So questions?
Thing like a high temperature expansion or in some effective temperature parameters.
Yeah, so here, so what happens is that, so this fluctuation dissipation ratio I showed, right? So in this model, right, so you can expand, so this I didn't discuss, so I sort of discussed only the, in your words, the leading term in the high temperature, but of course you can expand this further, right? So that will come down over here. So from this thermal transition, you can try to approach this here, but we have not done, but you can do it systematically. So it will be, yeah.
I mean, what I was trying to is, would you expect then that the thing that cuts off at h bar omega over T effective, would you think that that will now get higher terms in
so here in this model, actually there is only one extra term, right? So that that within the, okay, so what I understand, so this is within the variational approximation, right? So in the variational approximation, there is only one extra term, and that makes all the difference. So you are right. So let's say if I am not doing a variational approximation, and I try to do this, so it will be interesting to see whether there is other extra terms there. Yeah. Thanks.
Yeah.
Yeah, Sumilan, thanks for this nice talk. So this gamma, in fact, in your calculation plays an important role, which is the feedback, which gives rise to finite temperature. Without gamma, when you are doing this unraveling business at the average level, the density matrix is a standard Lindblad equation, and I believe the jump operator being Hermitian, it takes you to infinite temperature.
Yes, that's right.
So what would be the, is there an effective equation of Lindblad form when you
Yeah,
have this
I mean,
feedback?
we didn't write it, but you can write Lindblad type equations.
With the feedback?
Even with the feedback, yes. Yeah. I mean, we have not studied it much, but yeah, it can be written down. So people have written down with feedback a Lindblad equation. So there are literature on that.
So if you, without unraveling, if you study that Lindblad equation and look at this kind of phase diagram, I mean,
I think you will get same phase transition.
Same phase
So we are just studying it in this language. But I don't think there will be any difference.
okay, thanks.
What we are studying.
Other questions? So I have a small question. So in the same sense as mean field theory, right? So if you go to higher dimensions, the self-consistent approximation should get better and better, right?
Yeah, it becomes better, but although it is still quite bad near the phase transition, because it's like a phonon, right? So you are essentially expanding using the phonons of the superconducting state,
Right.
right? Because it's a harmonic approximation. So when the stiffness becomes small, then this approximation, even at higher dimension, is not good. So then it's probably better to do the mean field theory, single side mean field theory.
I see.
But single side mean field theory is not so easy with dissipation. It leads to a model which is hard to study actually, even in the single side level. It's like this standard instanton problem with dissipation.
Okay, I see. Okay, thanks.
Yeah.
If there are no more questions, and I don't see any hand.
Probably a naive question. So in the model, you had the delta theta coupled to the momentum of the particle, and x was measured.
Yeah.
So what's the motivation?
Why is momentum?
Yeah, why momentum?
No, you want something which doesn't commute with the state or the density matrix of the detector. So basically, it's like that what you are going to measure. So that measurement operation should not commute with the coupling. So then you get a non-trivial dynamics. So if you just couple with x, the dynamics will not be non-trivial. So essentially,
there is an intermediate time evolution, unitary time evolution that will.
So that in intermediate unitary time evolution, so that should be sort of non-commuting with the measurement in some sense to get a non-trivial dynamics. Otherwise, it is just multiplying. The measurement will be just multiplying some number. It's not going to change the superposition, if you wish. Okay, like so you want to do a thing that ultimately you start with two product state of the system and detector, right? So you kind of want to now mix, and then when you measure, then you already created a superposition in the position basis because of the momentum, and then you measure it, and that measure, as a result, you want a momentum or something which doesn't commute with the position.
Thank the speaker once again for the very nice talk.